Hello everybody, welcome to another video in which I try to explain physics as simply as possible but not simpler, and today we are going to solve another problem related to uniformly accelerated motion, actually uniformly decelerated motion. If you didn't, I recommend you to watch my introductory videos to this topic. They are here in linked and also in the description below this video. The problem which we will solve is inspired by the problem from Polish textbook. The name of the book is also in the description. Okay. So the problem is as follows. The driver of a car traveling at night at a speed of 54 kilometers per hour notices a fallen tree on the road and starts braking with a deceleration of 4 meters per second squared when he is 25 meters from the tree. Calculate the speed in kilometers per hour at which the car will hit the tree. Okay, so that's a really serious problem. So let's start with writing down the data, what we have. So the initial speed V0 is 54 kilometers per hour. We are supposed to calculate the final speed also in kilometers per hour, but the deceleration is 4 meters per second squared. So anyway, I would convert this into meters per second because it will be probably easier than converting this to to kilometers per hour squared. It's something weird, so let's do like this. You can check how to convert speed units and why like this in one of my previous videos. So I will here only briefly quickly do this. So it's 54, kilometer is 10,000 meters, hour is 4,600 seconds. So you reduce it and you obtain that this is 15 meters per second. This is the deceleration, and distance from to the point where the driver starts braking to the fallen tree is 25 meters. And in first part we are supposed to calculate the final speed. Okay, so let's start with the equation for acceleration or deceleration. So I remind you that this is the change in speed in time. So the acceleration is the change in speed divided by time, and our acceleration, or actually deceleration, is written as 4, so positive, so we should have positive change in speed. So we have to subtract the smaller value from greater value. So greater is initial speed when you slow down, when car is braking. So initial speed minus final speed divided by time. So here you have the V1 which you are looking for, but you don't know also t. T is also unknown, so you have two unknowns in one equation, so we need second equation. And we didn't use the fact that we know the distance to the fallen tree, so we can use the equation for the distance in uniformly accelerated motion. So distance is initial speed multiplied by time minus 1/2 at squared. So what to do? we are not asked what's the time of this motion, so we can get rid of it. So let's calculate. Let's get rid of time from, so calculate time from this equation. So if you multiply by time and divide by a, you get that t is v0 minus v1 divided by a. And this you can plug into this equation. So here and here. So what you have? You have that S is V0 times, so T is V0 minus V1 over A minus 1/2 A V0 minus V1 squared over A squared, so A cancels out a little bit, and okay, at this point you can plug in the values and calculate this just on numbers, or you can just also work with letters. I will go the second way. So to get rid of the fractions, which are always difficult part in maths, let's multiply this by 2a. So I mean multiply both sides of the equation. So here I have 2sa equals, so here a cancels out, but you still have 2, so it's 2 v0 times v0 minus v1 minus 2a cancels out, so it's minus v0 minus v1 squared. With this you have formula for something like this, like a minus b squared, or you can just think like squared means v0 minus v1 multiplied by itself, so you can multiply each term by each term and get the result. So let's see what's next. So 2sa I keep as it is. Here I multiply v0 by everybody inside, and with this 2, so it's 2 v0 squared minus 2 v0 v1, here minus v0 squared minus 2 v0 v1 plus v1 squared, and let's get rid of this bracket, so this minus applies to everything inside. So here is minus plus minus, and without this guy, and look, here you have minus 2 v0 v1 plus 2 v0 v1, so they cancel out. So what we have? We have 2sa, oh, and here is 2 v0 squared minus v0 squared, so it's just v0 squared minus v1 squared. Okay, and look, now we have everything. S is known, A is known, v0 is known, v1 is the only unknown, and this is what we are looking for. So let's just calculate v1 from this. So v1 squared is, I just move this to the left and this to the right, so it's v0 squared minus 2sa, so v1 is just square root of this. Okay, so now let's plug in the values. So v0 is 15, so it's 15 squared minus 2 times 25 times a, so 4 square root of this, and if you calculate this you get that this is 5 meters per second, but we were asked to calculate this as this is a speed of car in kilometers per hour. So again, like the inverse conversion, so it's 5 meters per second, so meter is 1/1000 kilometer, and second is 1 divided by 3600 in hours, so it's like 5 times 1/1000 times 3600 over 1, you cancel zeros, and you get that this is 18 kilometers per hour. So the car in this problem will hit the tree, the fallen tree, with speed of 18 kilometers per hour. Fortunately, it's not very high speed. Okay. Second part of this problem, calculate the braking distance of this car if there was no tree in the road. So the initial speed is the same, the deceleration is the same because it depends on the braking system of the car, and the question is, what's the braking distance? Okay, so perfect. These equations are valid because this is still uniformly decelerated motion. So this is equation for distance. What changes? We assume that there is no fallen tree in the road. So the braking distance means the distance until the car stops. So the final speed, when it stops, final speed would be 0. So here the change in speed would be initial speed minus 0. So it would be just v0 over t. Okay, so now similarly to what we did, t would be v0 over a, and we plug in this formula here to the time. So now braking distance is v0 times v0 over a minus 1/2 a times v0 squared over a squared. A cancels out, so you have v0 squared over a minus half v0 squared over a, so this is half v0 squared over a, or v0 squared over 2a. Simple formula for braking distance here. Okay, so to calculate the braking distance in this situation, you plug in the values. So s is v0 squared 15 squared divided by 2 times 4, so 225 divided by 8, and using calculator I obtained that this is approximately 28.1 meters. So you see that if the fallen tree was more than 3 meters further from the driving car, it would be able to stop before it would not hit the tree. Okay, and the last part, but as it is said, last but not least, calculate how many times the braking distance would increase, we assume no tree, if the car's speed was twice as high. So now initial speed is new initial speed is 2 times v0. So this we can just obtain simply from this formula for braking distance. So just braking distance when the initial speed is twice as high. So we just plug in this 2v0 in place of v0. So it's 2v0 squared divided by 2a. So 2v0 squared is 4v0 squared divided by 2a. And look, of course, v0 squared divided by 2a, it was this breaking distance, so this was s, and our s tilde is 4 times old breaking distance. So here is the important conclusion. If your initial speed increased 2 times, then your braking distance increases 4 times. So this is how the high-speed driving is dangerous, that your braking distance, so distance until you can stop with the same braking system of your car, increases a lot. So be careful when you are driving. And with this conclusion and suggestion, I finish solving this problem, and I invite you to next videos, and I also invite you to ask questions in comments to this video if you have any.